Hello, my name is Brandon, and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome. It is great to have you. If you are a returning viewer, it is great to have you back. If you like the video, please give it a thumbs up, share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. You can also find a link in the description below to all of my playlists. It's basically a table of contents. And of course, please hit subscribe and click the bell notification if you haven't already. So now that we are introduced, let's go ahead and get started. So this video is the first in a new playlist, which is always exciting. And this playlist is going to be about statistical model building. So in this first video, I want to change it up. We're going to do an introduction by demonstration. And what we're going to do is begin talking about a concept called GLM, which stands for General Linear Model. It is a family of statistical procedures that are all related. And we're going to look at the relationship between ANOVA, which we have learned about before, and regression. So we will spend the majority of the time in this video actually in Excel. And you can actually look in the description, find a link, and you can download the Excel file and follow along if you would like. So let's go ahead and jump in and start learning about statistical model building with GLM. So as I mentioned, this will be introduction by demonstration. So GLM stands for General Linear Model. GLM is an umbrella term for many statistical tests we are familiar with. So think of GLM as a statistical family. Methods such as ANOVA, linear regression, logistic regression, etc., are all special applications of this umbrella concept of GLM. So GLM allows us to build very complex models. And GLM is very flexible. So before we get too far into the weeds, let's have a GLM family reunion between ANOVA and linear regression. So let's go ahead and go into Excel and do that. Okay, so here we are in Excel. So the goal of this is to show the relationship between the ANOVA procedure and linear regression. So we have three tabs. In the first tab, we're going to do a one-way ANOVA. In the second tab, we will do a two-way block ANOVA. And then the third tab, we will do a two-way repeated measures ANOVA. And then we will pair regression with each one of those. So let's start here. In the upper left, we have our data. This data is actually based upon my one-way ANOVA video that's on my channel here. So we have 3 random samples of study skills assessment scores. So year 1 could be like the freshman year of 8 students. We have there in the first column. Year 2 could be, say, the sophomore year for 8 students. We have 8 values there, and then 8 students in year 3. So all 3 of these samples are independent, and they're therefore 24 random students in total. So what we're going to do is perform the ANOVA analysis on this data. So we will go to the data in our ribbon, data analysis, ANOVA single factor, click OK. Our input range is our table right there. Then we'll do group by columns, labels in first row. Output range is at A13. We'll leave that there. Then we'll click OK. So what do we have here? So first we have a summary of our 3 years. So the mean or the average for the students in year 1 was 70.75. For year 2, 74.75. In year 3, 77.25. That's basically the mean, well, it is the mean for each of the 3 columns. So look at our ANOVA table. We have an F value of 0.62137 with a P value of 0.5468. So our alpha was 0.05, our P value is 0.54. Therefore, we would fail to reject the null hypothesis. So now let's do the same analysis, but instead using linear regression. So look over here in the middle. Look at how I coded everything. Remember that for this, we're going to need 2 dummy variables. And the number of dummy variables that we use is always 1 less than our categories. So here we have year 1, 2, and 3, but we will only have 2 dummy variables, year 1 and year 2. So what we do is we put a 1 indicator variable for each score that in this case is in year 1. So that's the first 8 measurements. Then we do the same thing for the year 2 scores over here in this column. And then any score in year 3 gets 0 for both columns. And again, that's how dummy variables work when we put them into a regression model. So now, using this table, we can do our regression. Let's go ahead and do that. So data on our ribbon, data analysis. We're going to go to regression, click OK. So our Y's are our scores here in column I. Our X range are our years here in these two columns. Then we have labels in our first row. We'll leave output range checked to M1, which is up here in the top. Now I'm going to go ahead and add residuals here in this selection because I want to talk over those with you very quickly once we run it. So let's go ahead and click OK. And there we go. So now what about the comparison between these two? So first, I want to draw your attention to the total sum of squares for each method. In regression, our total sum of squares is 3078.5. Go over here to the one-way ANOVA. What's our total sum of squares? 3078.5. The exact same. What about the F statistic, or the F value? 0.62137. In regression, 0.62137. Significance level, 0.5468 on the regression side, 0.5468 on the ANOVA side. So actually, the ANOVA tables for the ANOVA on the left and the regression model on the right are the exact same. The exact same. So even the sum of squares for the between groups, within groups, regression residual, exact same. So very quickly, how would we interpret our coefficients over here on the regression side? Well, remember for year 1 and year 2, we would input our indicator variable depending on what the score is. So for example, if we wanted to predict a score for a student in year 1, we would have our intercept, 77.25, plus 1 times negative 6.5. So basically we have 77.25 minus 6.5. Year 2, that's a 0, so that zeroes out. And of course, year 3 would be a 0, even though we don't have that column there. So we have 77.25 minus 6.5. Well, what is that? Do that math out, and we get 70.75. Well, where do we see that in our ANOVA table? Right here. It is the mean of the year 1 scores. See how that works? What about year 2? So a student in year 2 would have a 1 indicator variable here and a 0 for year 1. So essentially would have 77.25 minus 2.5. That gives us a value of 74.75. And we have that over here in the mean of our year 2 scores. And then for year 3, we would have 0 for indicator variables here. So we would end up with just 77.25 plus 0 plus 0. Where do we see that? Well, that's the mean of the year 3 scores of 77.25. So you can see the relationship between the summary over here and how we would implement our indicator variables using the coefficients in our table in the regression. Now you can also see that in the residual output down here. So any student that's in the first 8, which are year 1 scores, would have predicted scores of 70.75. Well, that's what we calculated up here using our coefficients just in our head, and that's the mean for the year 1 scores over here on the left. And of course, for year 2, the predicted value would be 74.75, which is the same thing as the mean score for year 2 in the ANOVA table. So that's the relationship between the summary table, the ANOVA table, how the coefficients work with our indicator variables in regression, and how this is all tied together under GLM. Now let's do the same thing for the two-way block ANOVA. So here's our two-way block ANOVA. The one difference here is that we're going to assume that we have the same student across 3 years. So student is the blocking variable. So in this case, we have 8 students, and we're measuring their study skills assessment over the course of 3 years. I'll take a minute and look at how we coded that on the regression side. So for the year 1 and year 2, that's the exact same thing we did in the previous tab for the single factor ANOVA. Now we have 8 students, so we need 8 minus 1 student dummy variables. And then what we do is assign the student to whatever their score is. So here we have student 1 in year 1. So here is that value of 82, year 1, and then a 1 for student 1. Let's go to the next one. Let's just say this score here of 71. This is student 1, year 2. So we go down to the 71. Well, it is year 2. So we have a 1 indicator variable in the year 2 column. And then it's still student 1. So we have a 1 there. So all we're doing is coding this table on the left into dummy variables over here on the right. So if you want to pause and take a look at that very quickly, go ahead and do so, and we'll begin in a second. Okay, so let's go ahead and do our ANOVA analysis here in Excel. So we'll go to Data, Data Analysis. Now we want ANOVA two-factor without replication. Click OK. So our input range is our table that we have over here on the left. Then we have labels in the top row, alpha 0.05, output range A13. We'll leave that there. Click OK. So here we can see that we have a lot more information. So we do have our summaries for each student. So the mean here is the student's performance across the 3 years. So this first value of 72.3333 is the mean of these 3 scores along the top. Same thing for each of the other 7 students. And of course, the year 1 scores, the mean, are the same we had before from our one-way ANOVA. In the ANOVA table below, we have a bit more information. We actually have 2 F statistics, one for the rows and one for the columns. That's why it's a two-way ANOVA. We have 2 p-values as well to go along with those. Now let's go ahead and do the regression version of this. So to do our regression, we will go to Data, Data Analysis, Regression. Our Y range are our scores. Make sure those are highlighted correctly. Our X range will be our dummy variables right there. And we have labels in the headers. Output range, we will put right here, the bottom there. Residuals we'll leave checked. Click OK. And there we go. So let's take a look at the ANOVA table in each one. So look at the sum of squares total for both. 3078.5, 3078.5. The total sum of squares is the exact same. Now what is different, however? If you notice, the sum of square error of 2200 is the same in both. So in regression, we call that the residual sum of squares, which is the error. Over here on the ANOVA side, we actually call it error. So it's 2200. Those are the same. For regression sum of squares, we have 877.833. However, we don't see that over here on the left, but it's there. Can you see it? Well, if we take the sum of the sum of squares for rows and columns, we get 877.833. So it is there. But the ANOVA procedure splits it out into rows and columns because it's a two-way ANOVA. Now, because ANOVA splits it out, we have 2 F values or F statistics here. In regression, we only have the 1. So how do we get from this 1 over here in regression to the 2 over here, or vice versa? Well, the regression side is actually a weighted average of our mean squares. Let's see how that works. So if I go over here to the ANOVA side, let's just pick a cell down here, right here, and I do equals, I'm going to open 2 parens here, 7 degrees of freedom times the mean square for the rows, close, plus open, degrees of freedom for columns times the mean square for the columns, close both of those, divided by the sum of the degrees of freedom on this left side, and I get 97.537. We'll look at the mean square over here in regression, 97.537, the exact same. So how do I get my F statistic? Again, it's just division. So really over here, it's this combined mean square, or this weighted average mean square of 97.53 divided by the mean square error. So equals our 97.53 that we calculated divided by the mean square for the error, enter, and we have 0.6205, which is the same thing we have over here in regression, 0.6205. So they're related. It's all there. You just have to see where things are split apart in the ANOVA side and then where it appears in the regression side and kind of go back and forth, but it is all there. Now look at the residuals here. So if we wanted to do a prediction for a student's score, we would just input the indicator variables along with our coefficients here, right here. So the easiest one probably to do is for the student that got an 82 right here. So what we will say is that if everything is zeroed out right here, so 0 for year 1 and 2, that means it's year 3, and then zeroed out for the 7 indicator variables for student, that means it's student 8, which should be 82. So that student scored an 82. However, if we go down to our coefficients in the regression table and we put a 0 with all these coefficients down here, we'd end up with a predicted score of 75.33. Well, if we go down to our residual output, we will see that this predicted score of 75.33 had a residual, or an error, of 6.67. Well, if you add 75.33 and 6.67, you will get the score that they actually had of 82. Because again, the residual is the difference between what is predicted here and what they actually scored, which is here, 82. That's why our residual is 6.67. So we apply the indicator variables to the coefficients in the exact same way we did before. Now let's go ahead and complete this analysis using the two-way repeated measures ANOVA. So in this example, we've made one slight change and we put students into cohorts. So we have repeated measures. So what we have here is in cohort A, we have 2 students. We have year 1, so they're both year 1, and they're in cohort A. So we have 2 measurements in that intersection of year 1 and cohort A. Same thing for year 2 in cohort A, year 3 in cohort A. So to code that in the regression side, we did the exact same process. So here for this 82, this first student, they are in cohort A in year 1. So go to 82 over here. Year 1 has the indicator variable of 1. It's also cohort A. There's a 1 there. Now look at the 93. Same thing. Year 1, cohort A. And we could go on down this whole table. So again, we just assign indicator variables using the same methodology we did for the previous 2 tabs. Okay, let's go ahead and do our ANOVA procedure for this repeated measures. So we'll go to data, data analysis, ANOVA with replication. Input range is going to be our table over here on the left. Rows per sample, this is very important. This tells Excel how many repeated measures you have per intersection of your 2 factors. In this case, it's 2. We have 2 students in each cohort and year combination. So we'll put 2 there, alpha 0.05, output range, we will put down below it, May 13 again, click OK. So now we have a whole lot of information. I'm not going to go through this whole thing, but the thing we're interested in right now is the ANOVA table down here below. So you can see that we have 3 F statistics now. We have our cohorts, we have our columns, we have the interaction between the 2, and of course we have our error and stuff below that. So let's take this ANOVA table and compare it to what we get with regression. So we'll go up to data, data analysis, regression, click OK. Our Y range will be our scores right here. Our X range will be our dummy variables next to it. Labels, output range, we'll make sure it's down below there so we can see it easy. We'll go ahead and do residuals again so we can look at those and click OK. So I'm going to scroll down because we're really interested in comparing the 2 ANOVA tables. So what do we have here? Look at the total sum of squares. 3078.5, 3078.5. The same total sum of squares. Now you'll notice if I go back to the 2-way ANOVA, it's the same, 3078.5. That's because the data here is structured the same way. So we're looking at these 24 observations overall. If we go back to the 1-way ANOVA, the sum of squares is the same again. So there's a lesson here that when we're using these 24 values that are the same across the 1-way ANOVA, the 2-way block ANOVA, and the 2-way repeated measures ANOVA, the total sum of squares is the same for all 3. As long as we're using the same data, 3078.5. Let's go back here. Let's look deeper into the ANOVA tables for these 2. The way to start comparing these 2 is to look at the degrees of freedom. So in the regression side, our degrees of freedom for the regression part of our ANOVA table is 5. Well, if you look over here on the ANOVA side on the left, the 3 and the 2, those are the 5 degrees of freedom that are represented in the 5 degrees of freedom over here on the right. So these two things are related in the table. Likewise, the 18 degrees of freedom over here on the regression side correlates over to the 6 and the 12 on the ANOVA side on the left, which is the interaction and then the within or error degrees of freedom. So how do we get from these 4 sum of squares over here on the left, we have the 3 F statistics as well, 3 P values and so on and so forth. How do we get all that into 1 F value and 1 P value over here on the right? Well, we do that using the same thing we did before. So remember this, we're going to do the weighted version of these two values, and we should get a value that is the same as 143.7667. Let's do that. Go down here, equals, parentheses, 3 times the mean square for the sample, plus, parentheses, 2 times the mean square for the columns, close, close, divided by the sum of those degrees of freedom, which of course is going to be 5. Enter. And we get 143.76667. Same thing we have over here in the regression table. See how that works? Now we need to do the same thing for the other mean square. So that's going to be here and here. So below that, we'll do equals, parentheses, 6 times the mean square for the interaction, close, plus, open, 12 times the mean square for the error or the within, close, close, divided by the sum of those degrees of freedom, so 6 and 12, close, enter, and we get 131.026. Same thing we have over here for the residual or the error in the regression, 131.0926. Now to get the F value, we just do some division. So equals this value divided by this value below, enter, 1.09668, 1.09668. So you see how that all comes together. This is the beauty of GLM. These things are all related in intrinsic ways, sort of underneath the hood. And finally, as far as the residuals go and our predictions, it works the exact same. So if we go up here to this student, let's look at this one right here. This student got an 82, and they have zeros for all of their dummy variables. That's the easiest one to do, honestly. So if we do 0 times this number, 0, 0, 0, 0, we're going to end up with just the intercept, which is 74.33. If we go down, the predicted value is 74.33. Their actual score was 82. So the difference between 74.333 repeating and 82 is going to be a residual of 7.667. So the predictions work the exact same way. So to sum this up, we did this for a demonstration to show you that under the general linear model, these things are related. To show this, we did 3 different types of ANOVA, and we paired that with the regression procedure for all 3. And then we were able to see all of the numbers underneath the hood that are all related. And of course, we learned some other helpful things along the way. So let's go back to the PowerPoint and finish out this video. Okay, and we are back. So conclusion and next steps. So as you can see, different forms of ANOVA and simple or multiple linear regression are related. And this is just the beginning. So depending, pardon the pun, on the nature of the dependent and independent variables and research goals, GLM provides many tools for us to use. So in future videos, we will talk more about GLM and how we can use it to build robust statistical models. Great. So this wraps up this first video on statistical model building and GLM, or the general linear model specifically. So GLM is an umbrella term for many statistical tests. In this video, we looked at the relationship between ANOVA, analysis of variance, and regression, so simple regression and multiple regression. And as we saw, we got the same results using both of those methods. We'll stop here for now, but thank you very much for watching. Thank you for spending your valuable time with me, and I look forward to seeing you again in the next video. Take care. Bye-bye.